Okay, hello everyone. I'm Linda Peter. I'm a PhD student at Purdue University, working with Dr. Linda Lee, and my research main focus is on occurrence, threat, and transport of PFAS in agricultural systems. For today, I'll be going through the study that was done using a lysimeter to evaluate PFAS fate in a soil or in a field site that was reclaimed with exceptional quality biosolids. So just as an introduction, we are being told that the estimation by the US EPA is that 4.75 million of dry metric tons of biosolids were produced in 2019. And out of that, 51% of the biosolids were land applied. Now, there are a lot of reasonable arguments for why we should land apply biosolids, ranging from improving soil properties to improving plant biomass. Plants love biosolids, and this is all reasonable and is a way of recycling waste that we are generating. But the problem that we are having to deal with, and is more recently at least, is the issue of PFAS in biosolids. And this is because the waste influence coming into wastewater treatment plants that is being processed to biosolids come with different varying PFAS concentrations. And this ends up in the biosolids that ends up in the land application. So the question is, once the PFAS in the biosolids are land applied or PFAS is introduced into the soil through land application, what is the fate of the compounds or the several class of chemicals? And people have identified different pathways, and I'm just showing only 5 here. And we identified leaching as being a pathway, or soil attenuation of those compounds, or plant uptake of more mobile PFAS compounds, which could lead to bioaccumulation that is then being reintroduced to the soil as organic amendment. And all these pathways are being defined by the type of PFAS compound or the soil properties. So what we expect from a shorter chain is different from what you expect from a longer chain PFAS, and maybe your soil that has more sandy to clay ratio or loamy to clay ratio. So this all differs. For my study, I am basically focusing on the leaching pathway. And to do this, we used a field site that was artificially constructed. And when I say artificially constructed, it means that the field was excavated to 45 cm, and then it was filled with soils from sea horizon that was taken from a construction site. And this was done because we're meant to mimic a thoroughly degraded soil and how biosolids can help in reclaiming such soils. And because we filled up the soil with soils from the sea horizon, it was mainly clay's texture and had slope permeability. To have access to leachate, zero tension drainage lysimeters were installed 50 cm below the soil surface, and they were leveled, and leachates were continuously being monitored and collected from these lysimeters over the course of the study. So the treatments used were 4 forms of biosolids, and these were exceptional quality biosolids. Exceptional in the sense that the treatment process used in producing the biosolids went beyond the regular requirements for class A biosolids. So they had lower pathogen count and pollutants. Like heavy metals, I'm not talking about PFAS. So we had the biosolids. Another thing, because of proprietary reasons, I am not going to give much details on the type of on the names of the biosolids. So we have the biosolids that I'm naming biosolids, so because they didn't go through another form of treatment apart from the exceptional treatment I had mentioned earlier. And there's another treatment that was that same biosolids but blended with mulch. And then we had the heat-dried pelletized biosolids and the composted biosolids. And these were applied from fall of 2016 to summer of 2018. And in the fall, we had two types of application. We had one-time agronomic N rate, which is a regular nitrogen requirement. And then we had the 5 times, which was meant to mimic a land reclamation rate, like the amount of biosolids you might need to generate enough organic matter to reclaim a degraded soil. And then we had inorganic fertilizer that was like the control. Then leachates were collected all through this period, especially after a significant rain event. And this was limited to rain events that were higher than 2.5 cm. Once the leachate was collected and transported to the lab, they were spiked with isotopically labeled PFAS, processed through a solid phase extraction, and then concentrated to 0.5 mils before being injected to the liquid chromatography MSMS, where we would then quantify PFAS. So before looking into the results of the leachate, we would just quickly go through what we saw in the different biosolid treatments. And the highest PFAS loads were in the biosolids that did not have additional treatment, so no heat treatment and not composted. And then the rest of the treatments were quite similar in their PFAS loads. But what was interesting was that when the biosolids with the highest load was blended with mulch, we saw reduction in PFAS concentration, indicating that there was some kind of dilution through the blending process. So going forward, those are the two treatments we're going to be most concerned about in seeing how blending would likely then impact PFAS loads that will be seen in the leachate. So right here, we have result of PFAS loads in the leachate over the time of the study. And there are 3 things that we're going to be looking at is the temporal trend, the shape of the distribution, and the differences in treatment. As you can see, there was an initial spike for almost all the treatment immediately after application. And this we can attribute to not just rainfall, which I'm showing on top of the graph, but also to the soil condition, because I had mentioned that this was an artificially constructed site. Therefore, the soil structure had not fully settled after application. Then the rainfall came in, and then we saw a lot of these PFAS being released into pore water and then transported down to the lysimeter. Another thing we can notice is that over time, there was like some kind of tailing, and PFAS loads tailed off and was sustained by periodic addition of biosolids in the fall and in the summer. And for the treatment, the lowest in PFAS was the inorganic fertilizer, but we could just see a little bit of some points at some time, meaning that there might still be trace amounts of PFAS in the fertilizer. And the highest, as I would have expected, was the untreated biosolids that was applied at the 5 times agronomic rate. Now, squaring down on just the 2 treatments, that's the biosolids that was untreated, applied at 5 times, and the biosolids that was blended, the same biosolid blended with mulch, applied at 5 times too. So we can see that the concentration of PFAS in the leachate in the blended biosolids reduced, corresponding with what we saw in the biosolid extraction, especially for the initial spike that was seen in fall of 2016. And over time, there was the concentration gradually tailed and maintained some kind of level towards the end of the study. What was also interesting to note was the pattern of nitrate leaching for the same site during the same duration. We can see that, especially for the first quarter of the study, the pattern of nitrate leachate was similar to that of PFAS, making us think about if we had transport mechanism for nitrates that was similar for PFAS. I mean, normally when we think of nitrates, we think of them as stressors, not being readily absorbed, so they just move with preferential flow. So it would seem that at the beginning of this study, when our soils were still relatively young, if I might put it that way, preferential flow could have been one of the transport mechanisms, especially for the short-chain PFAS. And towards the end of the study, we did not really see such preferential flow because 2 years after, I would have expected the soil to have some form of structure and lots less macropores or cracks. Then when we look at the distribution of PFAS compounds in the leachate, as expected, it was mostly dominated by short-chain short-chain acids, both carboxylic acid and sulfonic acids. And for the two treatments, the distribution were similar. The difference is that for the treatments blended with mulch, the longer chain sulfonic acids were almost negligible. I mean, we could barely see anything that was higher than a carbon chain link of 6 for such treatment. Then we know, yeah, this is a leachate. We're not talking about drinking water here, but if we're looking at the EPA advisory limit of less than 70 nanogram per liter, and then we compare it to what we see in our leachate of PFOS and P4 combined, we would see that 65% of the time blending the biosolid with mulch resulted in leachate that had concentrations below that limit, while it was just for the other treatment that was untreated, it was just 18% of the time. And although I'm not showing it on this graph, only less than 4% of the entire composition of PFAS compounds were PFOS and P4, compared to the biosolids that were almost 30%. So in addition to being strongly adsorbed to the soil, blending the biosolids with mulch also reduced the amount of longer chain PFAS that was leached or released into pore water. So what's our major findings from all of this? Looking at the pattern of nitrates transport and knowing that our leachates were dominated with shorter chain PFAS, we are suggesting that preferential flow at the beginning of the study would have been a likely mechanism once the perfluoroalkyl acids were released from the biosolids into the soil. And then we saw that longer chain PFAS were being retained more by the biosolids and the soil, especially sulfonic acids. And most importantly, we saw that diluting PFAS loads in biosolids by blending with mulch gave us a corresponding lower PFAS concentration. And this is something that might warrant further exploration if we have to continue using biosolids as soil amendment. So ongoing studies is still on for this, and we are characterizing and quantifying PFAS in the soil samples, and we are also evaluating perfluoroalkyl acids in a biosolids, pore water, and soil water absorption coefficient. And I hope to share those results when we have them. So thank you, and I will be accepting questions.
The first question, was the mulch analyzed separately to determine the levels of PFAS?
Oh no, the mulch that was used for this study, we did not have access to it to analyze it. So we would assume that it would not have so much PFAS loads in it because we could have seen a corresponding increase in the treatment that was being extracted, which we did not see. So although we did not extract the mulch, we would assume that the PFAS loads were not, let's say, overwhelming enough for us to see any impact when we did the extraction and the treatment.
Okay. I am curious how mulch helps decrease PFAS concentrations.
Oh, it's more like a dilution, not a decrease. So, I mean, for this study, the ratio of mulch to biosolids was 3:1. So it's more of a dilution effect, not like a direct treatment effect. I don't know if that makes sense.
Okay. I apologize. I had a hard time understanding the source of untreated biosolids. Are they from an actual wastewater treatment plant?
Yes, they are. I just didn't include the treatment plants they are from for proprietary reasons, but they are from a treatment plant.
Did you note any pH effects in terms of the soil leachate?
No, we've not done analysis on the soils yet, which those are ongoing studies. So I have not done full characterization of the soil. For now, we just look at the leachates and the biosolids.
Do you know what was the blending ratio of mulch and biosolids?
Oh yes, the ratio was mulch was 3 to biosolids 1, so 3:1 ratio.